All right, so homework 3 is out, due November 18th. It should get you enough. The idea is to get you familiar enough with working with OpenCL that you can write something more complex, dealing with local memory, understanding throughput versus compute and balances like that. But hopefully not too much that it interferes with final projects. Final projects proposals send to me by tonight. Email the staff address. It's unclear if it's working. Actually, I think it is, but you can send them directly to me or to the staff address. And if you send something by this morning, I should have replied with feedback of some sort, whether it's just like, looks good, go. If not, ping me again, just to make sure it didn't fall off. I'll be going down the class list, making sure I have something from everyone there, but just to make sure. I'll try to get you early feedback in case something needs to be adjusted, and I'll ask you for that. I will get you by Monday whatever feedback is needed. There may need to be some adjustments, and I'll also give you your assigned TF, and you should plan on meeting with them sometime next week, and we'll set that up. Readings are posted for next Wednesday. There's a sort of choose which one you're more interested in. One that's more like how do you do physical simulation of interacting objects on GPUs efficiently? Because this is not something that it seems like maps well to the GPU structured memory, structured compute problem, but can be done. And one on tuning OpenCL matrix multiply. It goes through, here's the simple implementation. How do we make it more complex? And then a short reading, which I'm actually going to give sort of a very brief version of today on just how do you do fast transpose of an array in CUDA, which is similar enough to OpenCL that you should be able to see it. And it has the same sort of limitations. All right, finally, the Harvard Computer Science Fall Poster Session is on the 12th, which is right around when things are due, anyway, for the final project. Just a quick show of hands, who would prefer to do a poster there than to create a screencast for their project? Come on, hands, just trying to get, you don't have to talk about your group. I'm just looking for preference. All right, so maybe. Let me know if your group wants to do that, let me know. You'll get out of the screencast requirement. The poster session is right after class. So certainly I will head over there. Let me know soon. I'll post on Piazza as well asking about this. It doesn't matter to me. Either one is fine. The poster, you'll be expected to have a poster at the poster session and hang out for an hour and get snacks and talk to people about your work. All right. So today I'm going to walk through an example of some optimizations dealing with global memory, local memory, and some of the optimizations we've already talked about. It's to orient you towards the readings, partly, and just to show how these things change. So I'm going to talk about the transpose. We're also going to talk about atomics and talk about occupancy, which is the measure of how much latency hiding we do. So the first part I'm going to use, it's in the OpenCL examples repository. There's the transpose.py and transpose.cl. There are several implementations that we're going to iterate through in the OpenCL code. So what's transpose? Here's the transpose reading, actually, on CUDA. So transpose, we just take a matrix. In this case, we're only going to deal with square matrices. This code deals with the more general case of rectangular matrices, I believe. And you just flip it around its axis. It's a common operation. You often need to do it as part of some sort of linear algebra problem. And it's an interesting problem because it's very easy to code, but it's not compute intense. It's very much driven by or limited by the memory system of whatever GPU or whatever hardware you're running on. So this is the first version in that code. All right. It's wrong. It's fast. It calls it, and it's not wrong because it doesn't call itself transpose, but it's in with all the transpose people, and they're not sure why. And all it's going to do is I'm going to take some input, some output matrix. I'm going to take one size, n, assume it's square, and I'm just going to copy the output to the input. I'm just curious, how fast can I move a block of memory from one point to another point on the GPU? Right? Or on whatever code I'm running on. was going to try to run all of these on the NVIDIA K40 or whatever I have on my remote desktop, but I'm just going to show times rather than going through all of that. Okay. On the Tesla K40 for, I think the matrix in there is 4 megabytes. Someone can check in transfer.py. Takes a little under 1/5 of a millisecond to transfer. This is not actually that good. We'll talk about what good numbers are. It's okay. It's about half the full bandwidth. All right, but this gives us, this is going to be our baseline. Okay. All right, so how do we do transpose? We have work groups. We have some area they're going to operate in. They're going to be, they're going to tile over the input image, and they need to produce this other image where they transpose the data. And so it's basically just an axis flip, right? We flip about along the large axis. We also flip within our work group. So the most obvious way to code this is just, all right, we'll just change our offset math, right? So here's our input, our usual y times the width, however, whatever row we're in, and then however far across. And we'll just swap the meaning of x and y. Yes? Wait, what?
You're doing the identity matrix. You're just like...
No.
The output is the same matrix. Yeah.
No, the positions are different, right? Because the x and y position is different.
What you're saying,
right?
Yeah, but then
you're running it twice. That's what you're saying. Running it twice for each pixel, right? For a pixel.
Oh, sorry. We're not actually transferring in the. Sorry. When I said that we're going to flip in the work group and then flip. Sorry. It ends up by doing this we flip in both. Sorry. That was unclear of me. We're not yet doing anything within the work group in terms of flipping on local indices. We'll get to that. Right here, we're just going to use the global indices. Sorry, I got ahead of myself. So we're not yet worrying about work groups. We're just going to use the global x and y coordinate, swap their meaning, and write them back out. Okay? So it's going to be, that work group will write that location. But the code is correct, right? I think. I think it produces the right answer. It does. So here's the code. Transpose, global. So the output, right, the row and column of the output. Well, the input, so row is y, column is x. Yeah, so I read the y row, the x column, and I write to the x column, x row, y column. Let's verify. Excuse me, is this the same as 2 nested for loops? Yes. Looping over, is it 2 nested for loops over the entire x and y? Yes, because we're gonna, the global ID, I'm gonna tile. There's only one, I only show one work group, but I'm gonna have the usual math for, I'm gonna set a work group size. I'm then going to make sure that my work groups tile up to above at least the size of my image. Yes. Yes. It's not in place. Yeah. Oh, yeah. If it's in place, then it's much harder. Sorry. No, it's okay. It's okay. Yes, that's very tricky. Doing this in place, I don't think you can do. You can't do an in-place transpose in OpenCL because you have no control over when a work group will run. Right? It's quite possible that it'll schedule any work group, and that work group will finish, and then some other work group will run, and by that point, it's going to have overwritten its output. So. Yeah, sorry, yes. It's not in place. It's 2 different locations. So it's going to copy from one to the other. All right. I mean, I did have bugs. I'm not going to say that my code is perfect. And I didn't notice them until, luckily Wednesday was canceled. But I noticed them at I noticed them when I woke up at 2 a.m. because I have kids. I was like, wait, oh, that's wrong. And my debugging had been to print the upper left. It's very easy to do the transpose in the upper left if one work group does its transpose and then writes it back. But all of I had done every work group just transposes locally, And if you look in the upper left, it's perfect. And if you look in the lower right, it's perfect. And if you look along the top row, you're like, well, that's not so good. But let's run it. I mean, it's, I need to switch. So right now it's using transfer. So I got up and fixed it, because I can't sleep with that. All right, so now we use the transpose. All of this is the usual whatever code, the usual boilerplate to set up a tiled image. We're going to use workgroup size of 16 by 16. And now we'll use the transpose. Okay, so those should increase by 2,000 as long as it gets like 3,800 at that point. All right, this is on this machine, my laptop, so it's not the numbers I'm going to show for the K40. All right, so that works. Okay, what's the problem with this approach, though? All right, so this takes, so the last one was 0.19, and now we're up to around let's just talk in hundredths of milliseconds. Last one was 19, this one's 31. Okay, so a serious hit, about 50% slower. Yes? In this case, I expect the input reads to be coalesced. OpenCL doesn't specify in the standard what layout X versus Y should be consistent, and doesn't even necessarily talk about coalesced reads. But I expect that X varies faster. Maybe not. One of these is coalesced, yeah? Either X or Y. So, but one of them is not, right? Right. One of the, so let's assume that X is the thing, right? Well, so one of them is not. Let's try to fix that. Right. We want this to happen, right? We want to do a read in sequential threads. We want to do a coalesced read, move to local memory, and then do a coalesced write. Right, this is what you're saying. Okay. So that's this code. Now it gets a little bit ugly, right? This is what we've seen with buffers and halos and stuff like that. We'll do the transpose, so we get a local buffer. The transpose happens here. The local transpose, right? When we read, let me go back to the picture. Did I draw that correctly? I did, good. So when we read, there's nothing about locals, there's nothing about local memory that says we have to do coalesced reads or writes. So we'll read the 1, 2, 3, and that thread will write. I mean, those threads will write in this order. And the transpose will just happen in local memory. And then we'll write it out that way. And the way we do that is, right, well, we get the buffer size so that we know, we'll assume that the buffer is the size of our, or the buffer width is the size of our workgroup. We'll do the transpose here. You can see the inverted logic, right? We use LX as our local index, and we're offsetting by LY instead of by X. Barrier, yeah, so to make sure everyone is done. And then there's this thing. What is this base? People remember from the arrows going everywhere, or figure it out from the code? What is base in terms of, it's a coordinate transform. What's X minus LX and Y minus LY? Remember? Top left of, I mean, there's all kinds of top lefts. This one is the, X minus LX is the, sorry, it's the distance of the top left of our local group from the global image. So that's our base, and then so we offset to base and right here, and then all this is just indexed within the, offset from that point. Right, so that everyone knows where they need to write. It's the corner of, it's where the 1 is in the output buffer. And then everyone else just indexes off of that 1 to make their lives easier. And then again, we're we're indexing right here, Ly, Lx, and we assume that Lx is our coalesced direction. Okay, first thing, does it even work? So, transpose local.
Why it's coherent for the reading for the writing?
Here, let's talk about that. So, our assumption is that x, the global ID 0 coordinate, our x coordinate is our coalesced direction. It depends on the hardware and how they've implemented it. I don't have the full code here, but we assume that 0 is the coalesced direction. I haven't actually tested that, and I probably should. So if we assume that this is coalesced, right? We assume that's coalesced. This is a local memory write, right? We don't care what direction we write here, right? There's no coalescing, because buffer is local. Local is on chip and fast. It's the far.
So we can do a vertical.
So we can write vertical columns. So we can write horizontal columns. We can write diagonals. We can, yeah, and we don't care about coalesced access to local memory in general, or at all as far as I know. And then this again is a read from local memory, so we don't worry about coalescing. And this Lx is varying in the same direction as x. So if x is coalesced there, then this write is also coalesced. Okay. So now we just need a cl.local memory 4 times work group size. Right, our work group size, that's defined right here. It's just the size of our work group. We just need a buffer the size of our work group. And now we're using, what's the name of it? Transpose local. This is going to make sure that it works. I don't know if it'll be faster. No. This hardware is not, I mean, it's quite possible my transpose direction is actually opposite on this, and I've made it slower, and I should switch to the Y direction. But I haven't experimented like trying to tune to this at all. But the answer is correct, so at least that's good. All right. So those are the changes that, well, those are all the sort of coordinate changes that we needed to do. All right. On the Tesla, now we're down to 28. So it was 19, then 31. This shaves off about 10% from the slow version. Which makes me think actually the coalesced direction, I didn't have time to experiment more with the direction. I think the coalescing direction might actually be opposite this. All right. So we've improved it this way, right? We read by sequential threads and we write by sequential threads. We don't care about coalesced directions in local memory, but what do we care about? Yes, we care about the coalesced reads exactly to the global memory, right? And we fix that here, we think, we hope, right? We read that one in that order, we transpose to local, and we write coalesced.
So when you're writing, that's done by the driver and not by the individual threads.
When we're writing.
When we're writing global, that's not part of the thread that you showed, right? That's not part of this.
It is. It is. So this is the first arrow. Move from input to the buffer.
Right. So when you write, okay, so I see where you're writing to global. But how can you guarantee that those will happen sequentially if they're each individual thread?
How do we guarantee that they happen sequentially? It depends on the hardware that they map to. So if we're running on an NVIDIA, the way it works is you have your threads in your work group are chopped up into 32 thread groups, sometimes which is called a warp. And you'll see this in the CUDA reading. And those run in lockstep. Those are like AVX, but everything is like this. Those 32 threads, you may have a work group that's larger than that, right? In this case, we have 16 by 16. But 32 of them will be stuck with exactly the same program counter They'll do the masking trick if you have any conditionals, where we check here. Some of the threads might go to sleep until the if condition finishes. And so when they read from memory, they all read from memory at the same time. And if they read from memory in a contiguous block, it costs the normal wait time for that. If they read scattered or different, if they read a column, then they get serialized. The first one gets its answer, then the next one gets its answer.
Right. So the way that they're initialized is going to be, like the threads are going to be in order, but then you're going to put them.
Oh, you're asking how I flip to write out. I flip LX and LY. I think you're asking how do I change the order, right? Because they read in this order, right? There's
The threads maintain a constant order of execution if they access shared pieces. Because they can only write one at a time for.
You're asking if they access scattered memory, they read one at a time?
Yes.
It's more like they have 32 of them running together. They issue a memory read, and they stall until all of them finish. So if that memory read can be done in a single exchange, if it's 32 contiguous words, it'll go to memory, it'll take some time, they'll all get the answer at once and they'll continue. If they read scattered values, it'll get serviced as a serialized version, basically. One of them will get an answer, the next one will get an answer. But they'll still wait until all of them have an answer. It'll just take a long time. It's just the memory subsystem is you wouldn't. Does that explain? Or are you asking about this?
I think I understand. I was asking specifically how, like, okay, so you have a group of coalesced threads for the first row.
Yep.
Coalesced threads for the second row, and a group of coalesced threads for the third row.
Yes.
And then you're gonna read all of those in.
Mm-hmm.
So it's gonna take three different reads.
Yep.
Then you're gonna transpose in the buffer.
Yep. Well, I read them in and write them transposed.
Yeah.
Right.
But then you bake it and you write a different pixel for each thread.
Right.
Based on their order.
Right. But here's where they still end up in the same order for writing. So the thread. So I think I understand. How did I swap them so that 1, 2, 3 there reads in order, a coalesced read. How do I make those then write 1, 4, 7? The answer is. So here, right, when I read, I'm indexing by, the fastest variant index is by X, right, the global X. So this is a coalesced read under our understanding of this, right? But it writes transpose. But dealing with buffer, we don't care about thread order, right? Because this is local memory, so coalesce doesn't matter. I then change I just swap their LX and LY. Well, what they take from the, right, so I already did the transpose, so now those top 3 read from the top row of the local memory. The local memory's already been transposed. So now it's just read the top row and write the top row. And so at this point, these 2 reads and writes are by the top row, are coalesced again. Is that explained? Okay. The buffer size doesn't have to be, no, it doesn't have to be square. In this code, the matrix has to be square. You don't have to have that. That requirement is relaxed in the NVIDIA code. The NVIDIA code, I'm doing this because the NVIDIA code that I'd like you to try to understand is kind of complex it's more complex than this. I want you to understand what it's doing though. And that will you should be able to understand the simpler version. Because the NVIDIA code does a few things to speed it up. And also has doesn't require a square matrix. It'll transpose a rectangular matrix. Okay. But that question is good. Does the buffer have to be square? Do we want it to be square? Right? This is our first step. What do we have going on here? What do we care about in local memory?
I just have a question for
Oh.
this one. So what's your setting for the working? Do you set it to the size of the book?
I said it's a 16 by 16. It's not necessarily the best choice, but but also the way I've written this, I can't do rectangular work groups, which the other code also does. It uses a 32 by 8, I think.
But why don't you set it to 32 by 32?
Because if I do it 32 by 32, I run out of resources. I cannot actually schedule all of the threads. Which is unclear. It should be able to handle this. It's an OpenCL limitation, I think possibly just based on the version I have.
So last class we talked about those, I think, serialized reads when like multiple threads would be trying to read from the same memory register or something. Do you do anything to fix that here? Or?
It's exactly the problem. So what did we call that? Do people remember what that was called when dealing with local memory?
Oh, I didn't know.
Serialization is the bad thing that happens. This happens in global and in local memory. Bank, right? There's 32, usually in GPU hardware, there's a bank, or the memory to make it fast. We use parallelization, just like everything else in this class. And the way they do this, you have 32 bits are stored in one bank. The next 32 bits by address are stored in the next bank. And if you try to access, your access pattern can easily be such that this and this are in the same bank. And so when you try to write to both of them, it gets serialized based on which bank it's going to. And in fact, our work group here is 16 by 16. And so we know the first element here and this element and skip 2, we're only actually touching 2 banks by default if we use a 16 by 16 buffer. What was the fix? So, right, let's just do this, right? Tack on our extra row, which we don't use, or extra column that we don't use. We just allocate it. We do we change our math a little bit. In fact, it's a single line change. Right here. Assume that our buffer is 1 wider. Right, now we go to different things. Okay, we have to make 2 changes. I guess it's 2-line change. So right here we do avoid conflict. And here we need to, oops, the column size is the local size. Okay, so we just add on 1 column. So we spend some resources here. We use some extra local memory. But then the code itself just has this 1 change. And when we go to run it, did I save that? No. Just to make sure it still works. It's not any faster. In fact, it's a little bit slower on this hardware. Again, I'm tuning for the wrong machine. But it does help on the NVIDIA, slightly. Now we're down from 28, 20 down to 27.
You didn't add one at the local.
So I add 1 here. This buff size is not actually the size. Sorry, that should be buff width. Right? I say the buffer is 1 wider. I only use buff size. I use buff size here, right, as its width, and I use buff size there as its width. I need to add a column's worth. So in the allocation, I allocate my work group size was the width was just the width.
In the second one, it's width.
What's that?
Is it the width also for the second?
It's also the width here because this is row times width plus column. Right. Whenever you see this sort of, and you know that you're accessing images, row times width times column, or.
But then in that case, we interchange, right?
Well, that's the transpose trick, right? Yeah. This one writes a transpose thing, but that's because we're using x as the row to write to. The buff size is still the width. Okay. All right, so how slow are we? We're dropping it down. We're getting closer to, optimal would be, to get down to 19. With some more experimentation, I might be able to get this to do that in this form. It's not the optimal way to do a transpose. From here, you'd have to go to non-square work groups, and you'd want to actually do more work per thread, because there's a lot of computation we're doing which is done by every thread, which could be reused, a lot of these offset computations. And when you read through it's a really short reading, this CUDA stuff. It's only got like 3 or 4 kernels. On the K20, they say, okay, there's a copy. Let's do a simple copy, like I did, the transfer. and this is our bandwidth. 136 gigabytes a second. If they copy through shared memory, it's faster. Right? Without that many other changes, just let's move it to local and then move it out. It's a lot faster. Because when you copy direct, you've got, there is actually, I've been saying, GPUs don't have caches. They have some caches. I've been lying, sorry. You caught me. There is a little bit of a cache. It's not a very smart one, but there is some cache. And so when you first read it to local and then write it out, you get less cache thrashing. Basically, a bunch of them are reading. You reuse the data, and then they all write it out. So the fastest is actually to copy through shared memory. And then they actually get, with the no bank conflicts, they get faster than the naive copy overall. This is basically the last version we did, where let's move to local memory, let's offset it by 1 to avoid bank conflicts. The OpenCL code I used, the transfer is nowhere close. It's only about 50% of the optimal bandwidth.
So shared memory is different than local memory, right?
Sorry. In CUDA, shared means local in OpenCL. So shared and local are the same. Shared doesn't mean anything in OpenCL. And it's called shared in NVIDIA land, but it's a poor name because no other threads can touch it except in your own work group. So now, I was talking about those 32 threads in a warp on NVIDIA hardware. The work group can be larger than that, but you get constraints where since memory is shared within a work group, if your work group size is larger, they all have to be on the same compute engine in the NVIDIA hardware. And so it starts you start getting problems with occupancy. All right, that should orient you towards the reading enough for it to be useful. All right, debugging kernels. There have been some questions about this. The answer for OpenCL is it sucks. Because it's all very vendor specific. And since most of the hardware out there is NVIDIA, and NVIDIA doesn't necessarily care as much about OpenCL as CUDA, the tools are worse. So CUDA has CUDA GDB if you're working with CUDA. AMD implementation of OpenCL, you can emulate the GPU on the CPU and debug it that way, so you get exactly the same behavior you would expect. I don't expect you to have to deal with any of that. I hope you don't have to. You can use feedback buffers, right? You can store values pass in an array, set the value to something and read it back. That's kind of painful, but you can use printf. I mean, you'll just print to the console. I mean, what could possibly go wrong, right? Let's just do this. Here we go. Let's go to transfer, right? Go back here. I'll go back. Don't mess up my flow. Missing a what? Fine. All right. This is a good idea. Should I run this? What could possibly? So it's possible that the lecture will end here when I can no longer use my laptop. Go. What's going on? How many printfs did I just execute? Good. How many printfs did I just execute? 2,000 by 2,000. Right? Be careful, right? Let's make this a little bit saner, right? So that's the thing. You're in billion thread land, right? Every time you call printf, every thread's like, okay. And it locks it has to talk to the CPU, it has to do all this stuff. Let's make this a little more sane. If x equals. X a little better, right? Let's make it a little bit less noisy. What? I don't need curly braces. I'm only doing it for one. I don't need any. I probably didn't want to exit that. There we go. Oh, that's right, and I do it a bunch of times. That was the other thing. I looped like 250 times. All right, better. So use it carefully. Use, check LXLY. Only print one per group, or only for specific values, only in very limited cases. So it's possible, it works. It's actually not that bad. It's kind of nice to be able to print from your kernel up to, and it'll work on NVIDIA hardware or anything else. But do be aware, every thread's going to do whatever you tell it to. All right, I want to talk about OpenCL and atomics because you need to use them for part of the homework. And they're sometimes useful they may be useful for final projects. You have a bunch of atomics. Atomics basically are, they're built-in lock protected resources. What happens is you say, I want to atomically increment or add something to a memory location. The memory system locks that location until the operation is complete, and then gives you back usually the previous value. And so if someone else comes in and, if another thread comes in and tries to modify the same value with a different atomic, it won't be allowed to. I don't know if another thread can just use a non-atomic operator. But if you have certain variables that are only accessed with atomics, then it will work. You have various things, exchange, increments, taking the min and max. You'll have to use some of these on the homework. Documentation is online. They're pretty simple to use. Just be aware they serialize, and they're slow. You don't want to use them in general if you can avoid it, because again, only one thread can be accessing them at a time. Right. So if we were trying to just count the number of threads, the top one will almost surely return far fewer than there actually are. Right. It's going to go to the memory. Oh, it's going to fetch back whatever the value is in memory, increment it, and write that back. All of that's going to overlap with each other. You're going to get something much smaller than this, which is guaranteed to give you the correct count for how many threads you've launched on this kernel. It's going to take a lot longer, though. I encourage you, if you're curious, to try these two. Which one's fast? How much slower is the first one, or the second one than the first one? How inaccurate is the first one? Yes? Global. I don't think you can do them on local. I haven't tried. I know they work for globals. I don't think they're implemented for locals. For locals, you'd usually just do locking through thread ID. Global accesses are not necessarily, no, global accesses are not serialized. They're serialized in the sense that the memory subsystem will only serve up one thread's worth of, one work group's request at a time. But that's two trips to memory, right? One to get the value, a count. One to write back an increase, right? So those are what get interleaved and start writing over each other. This one locks, or if the memory system is smart enough, does the increment remotely in a single operation. But I don't think there's any hardware that does that we deal with. So, like I said, they're slow. Yes?
So the first was wrong because of what we were talking about during locking?
Yes, exactly. There's no lock there, right? And since it's two trips to memory, you're going to get, all of you read the, if all of you go and fetch a number from the board, and then your task is to go and write 1 plus the number you saw, and you all just start at once, whatever number I put up here is going to increment just a little bit because everyone's going to see it roughly at the same time. Make sense? Okay. So atomics just have the built-in locking for some limited operations. All right, occupancy, you'll see this word if you do any CUDA or more OpenCL, if you do GPU programming. It's basically the GPU term for how many, we've talked about it before, how many threads can we host on the hardware at a time? GPUs use, the higher the occupancy, the more latency hiding you can do. But it's limited by context size, the registers, the local memory, whatever else. It can be measured statically, particularly the NVIDIA compilers give you a lot of feedback about how many, you'll say use this many registers, this much local memory. You can plug it into a calculator that says you'll run this many threads. And AMD also has tools, but they're not built into OpenCL, and it's kind of unfortunate. But we can do it with atomics. Right? If you're curious about your kernels and want to know how effective they are, you can get the empirical occupancy. Have two global integers. They initialize to 0 when you launch your kernel. One is the active count. How many threads are operating right now? And one is the max that it reaches. And then you just need this code, right? When I start up, I'm an active group. I'm only going to increment it for my work group using the local ID. Increment the active number of work groups, and then check if I've beaten the record, right? Atomic max is the max active. And then at the end, decrement. And I think I have code that does this. Oh, yes. Transposed. It's in there. I'm not going to run it right now because I'd have to change the Python a lot to get the two counts in, but it's in the examples code, and it's not very good on the part of the reason that the transpose code is so poor on the K20 that I was running on, or K40 I was running on. I only get like 48 threads out of 48 times 15 or whatever the hardware can actually host. One of the main fixes is basically keep the threads around longer, and that's something they do in that write-up, or in that article. What's that? It's not that I only have access to that many, it's that they are so short-lived, right? They do a read, they write in local memory, and they write out. And so a lot of them finish while the other ones are still waiting for memory. And so they never actually get that much, they don't hang around for that long. And so there's not a lot of, they do a lot of wasted computation as well because of that. Because they do a lot of indexing tricks, read a bit of memory, and then write it back. The CUDA code does a lot more work per work group, per thread even. It's responsible for a whole column's worth of transfer, or a large number of blocks. So it takes a little bit more to parse it out, but instead of just doing one block, it basically marches down the column and does each of them and reuses a bunch of the computation. And also keeps them around longer. So if you have more threads, if they're longer lived, they can overlap more. Okay. All right, so next time, I want to talk a little bit more about OpenCL CUDA translations for people who are going to be doing CUDA. Yes? Yep. Why am I incrementing twice? You mean at the top and the bottom, or at the top? So that old +1, atomic inc returns the previous value that was there. So that's why there's a +1 there. Because if the active was 0, I'm going to get back a 0. I'm going to write 1 into active. But that's just what atomic increment does. All right. Yeah, it's about 1/15 of optimal. So in general, especially for simple kernels, you want very high occupancy. You want a lot of latency hiding. There are cases. I'm going to post something else. I'll post it in the readings thread, though it's not really part of the readings. There are cases when you actually can do much better with low occupancy rates, because depending on how you're interacting with the memory system, there's a paper and a talk that I'll link to there for people who are curious about, sometimes it's not worth increasing occupancy, it's worth doing more computation. Particularly on computationally intensive tasks, occupancy doesn't help you that much. It's better just to, get a little bit of latency hiding and do more compute. And so I'll link to that. It's interesting, but it's a little bit not that germane to this. All right, so I'll talk a little bit about CUDA for people. There are a few people doing CUDA projects. If you're interested in GPU programming, OpenCL is cool. It lets you target CPUs, things like that, and target a bunch of different hardware, but eventually you'll probably have to use CUDA because it's basically the king in this market. I'll talk a little bit about future directions for GPUs. There's some very interesting changes coming on the horizon. And then on Wednesday, we'll do the OpenCL readings, and probably an OpenCL review as part of that as well, depending on what the balance of questions is. So if you have questions related to OpenCL or CUDA or GPUs or whatever, post those in the readings thread, and we'll deal with those whether or not they're relevant to the readings themselves or just to the class and what we've been working on, what we've been talking about. All right, so for those of you who may have come in late, if you sent me a proposal or a pre-proposal by this morning sometime, I have replied, except for at least one case I know of. If you haven't heard from me in that case, and you have sent me something, ping me again. Do send them by tonight, and I'll get you feedback back by Monday. All right, have a good weekend. Oh, wait, homework is due 18th? Is that the number on the page or +2? The number on the page is the 18th.